Now let us go through the startup file for our controller. So we have named it startup_gcc.c, and we have seen this file being used in our make file. In this particular segment, we will talk about the contents of the startup file and how to write a startup file. So we will not be writing the file from the scratch. I'll provide enough information to you so that you are able to write your own. So there are some sections that the startup file will contain, and as you know, the job of the startup file is to boot up the microcontroller and bring it to a certain state, after which the other peripheral initialization routines will be called in within the main. That is the mechanism for startup here. It could be done otherwise as well. So the main job of the startup file is exception vector, sets up the exception vector table. That is the first job of the startup file. Secondly, it runs the reset routine. So it runs the reset function, or the job of the reset function is to move the initialized data from, and we talked about this. So reset function moves the initialized data from the end of the text section into the RAM. So this is the RAM and this is the flash. So it moves whatever initialized global data we have here, it moves it to the RAM, because that cannot be, this RAM, since it's volatile, once the processor is powered down, this data is lost. So it has to be retained somewhere. It is there in the flash. At every startup, that data is moved to the RAM, and this is the job of the programmer. So this is done by code that you write. Also in the reset function, we have to zero out the BSS section. So whatever BSS section we have to zero it out. And in this special case, we have the BSS section not only contains the uninitialized variables, it also contains the stack space. So this entire space has to be zeroed out by and this also has to be done by the code. So we will see all of this. So we will, when we come to this particular function, we will see the code here. Now we will go through this file line by line. So this is this, and it also contains some default functions to trap some interrupts, and also some fault ISRs and so on and so forth. So it contains the NMISR, fault ISR, and it contains the default handler. Okay, so we will have a look at these individually. Now, first of all, we include some header files. One is the memory map header file, and the other one is the core initialization header file. Okay. But we don't use anything from the memory map header file as such, because we are not really accessing any register here in the startup file. But we include these header files nonetheless. And then we do some declaration for the functions that are there in this particular file. That is, reset ISR is one, NMISR is another one, fault ISR, and then we have the default handler. Default handler is for those interrupts in the exception vector table where the interrupt routines have not been actually written. So in case such an interrupt is enabled, and it just goes into the default handler and it gets trapped there. We'll see that. This one is an unsigned long, that is array of, and it is known as PUL STAC capable stack. Okay, so this is the stack space for this particular controller, and you can adjust this value. This is a user created array only. Now this array has 256 elements, so it means it has 256 words. So 256 words. Okay, so 256 words would mean 256 into 4 bytes. And we saw the space occupied by this array in the .map file. So now this is one of the most important parts of a startup file, and that is your interrupt vector table. So this has to be set up very, very carefully. Now the interrupt vector table is set up in different ways. Since Cortex-M allows us the liberty of writing the entire startup code in C, because its interrupt mechanism has certain features which allow us to just mention the function calls here, that is mention the function addresses here rather than jump addresses. If they were jump addresses, then we'll have to write them in assembly, but here it is just the function calls. So we can exactly write it according to the memory location, the way it should be written. For example, each of these will occupy some space in the exception vector table, and these function pointers and data have to be mapped exactly the way this processor expects it to. For example, each of them will be occupying a memory location, and for example, the sysdig handler has to occupy a particular offset from the beginning of the flash, and of course this exception vector table will be coming in the beginning of the flash memory. This is where the processor wakes up and starts its execution from. So now we'll have to go and have a look into the reference manual and into the exception vector table. Now this is the vector table that we have to put into the startup file, and as we see that the first one is reserved, so here we will have the address of the stack pointer. Okay, so this one will contain the address of the top of the stack pointer, that is the highest address plus 1 of the stack pointer, and then we will have the address function for the reset handler, and then we have the address for the NMI or non-maskable interrupt, we have the address for the hard fault, then the memory management, bus fault, usage fault. So we talk about all these interrupts in detail in the interrupt section, so we will talk about them in a lot of detail, but for now just know that these are memory locations. So these are 0008, 0000C, so 8 plus 4, 12. So these are all 4-byte locations, as you can see. All are 4-byte locations. So it starts from 0, then it goes up to 4, and then 8. And they are not continuous. There are some gaps in there also. So what used to happen previously is, before ARM Cortex, if we had to have in C, it wasn't possible to actually write a jump address and expect it to exactly occupy 4 bytes, because it would have had to be probably it would have to be a function call, say. And if it's a function call, then that might translate to anything. The number of number of bytes that could be occupied by the function call could be different. Here we have to confine it within 4 bytes, and we'll have to mention the function pointer. So we can do it with C itself. And one more thing is, if you have an array of say you have to call a function. Say in other older processors, we probably have to call a function, and then we have to call the function here. Now this may translate to a branch bx instruction or anything bx or bl instruction, but when we have the next function, say we make a function one for the call here, that is maybe that is how your previous ISRs needed to be called. So suppose you have you're calling the NMI, and there's a function call for the handler here, and then you do a call NMI. Now, all these functions, we could actually have those function. We just could have all those functions in an array, but how do you encapsulate function calls in an array? We could have function addresses in an array, but suppose if you have a function call, okay, it is not possible to have the function calls enclosed in an array, right? So you cannot do, say, a function 1, then function 2. These are calls. I'm just saying these are calls. These are not function pointers, and then enclosing them in an array is difficult. What could have been, because and if you declare these functions one after the other, you never know how the compiler is going to place these functions. Okay, it could be placed anywhere, so it may not be placing it one after the other, say occupying 4 bytes only. So previously we would have to write assembly here, but in the case of Cortex M4, the benefit that we have is Cortex can understand the function pointer, and it directly jumps to the function pointer without an instruction to jump to the function. So if you mention a function pointer here, Cortex will jump to that function. It is not a call, it is just a function address, and it knows that within this exception vector table, and it finds a 32-bit value here. Say it finds a 32-bit value here, it will consider that value as a function address, and it will jump to that function. So you really don't need a function call in the case of Cortex M4 exception vector table, and that makes it easy for us to encapsulate multiple function addresses within a data structure. And when that happens, we can keep the alignment, and we can have the right function addresses in these places, and we'll see how. Okay, so this is the exception vector table, and this exception vector table needs to be written in that startup code. So how do we do it? As I mentioned, there are various ways of doing it. One way is what we have done here. Now, in the beginning of this section, as you can see, there is an attribute added where we are naming this section as a .isr vector. Okay. And we saw this, we spoke about adding extra sections in the linker. So when you have the linker here, you see that there is a .isr vector added here. So this section, this data structure, whatever we will talk about now, definitely goes and sits on the top of this linker, or it starts from this particular memory address, which is our intention. No matter we could shuffle around other things, we could put a gap here and all that, but this one has to be fixed, the ISR vector. Now, how is it organized? So first of all, we see that we named it as a section. Now this section name could be anything. Whatever section name you have to put it in the linker script. And as a side note, whatever we had studied about the linker, I did not have an align statement so far. But here I have put an align statement in the BSS section just to be on the safe side. So you might find a discrepancy when you are looking at the old linker or the previous linker videos that we have gone through, and and this one, the difference will be there is an alignment here. There is a 4-byte alignment. Generally, it is aligned by the linker, but to be on the safe side, I thought that it is better to put an align. So align is generally with the align command, and in brackets whatever how many bytes you want to align. So dot equal to align, it means that the first address whatever of the BSS section is going to be aligned to a word boundary. So if it's not aligned to a word boundary, it is the linker is going to add that many bytes, so that if it's already aligned, it won't touch it. If it's not aligned, it is going to align it to a 4-byte or a word boundary, and then the BSS section is going to start. This is important in this case because the stack is a part of the BSS section, and the stack definitely needs to be aligned to a 4-word boundary. A stack needs to be aligned to a 4-byte boundary or a word boundary. Okay. So that is the reason I had put align 4. So if you see this discrepancy, this is why the align command has come in here. Moving on. So you need to have some knowledge about function pointers here. This is how you define an array of function pointers. So this is an array of function pointers of type void. Okay, and these are the name of the array is g_pfn vectors, and it's constant. So it's a constant data here. Okay, and it's a global. From what we have learned, a constant and a global data, it goes into the flash memory, that is the read-only memory. If you remember, because it's constant, it's global, it's initialized, and it's a constant. Constant means these values don't change. These values will, once it's set up, these values will not change. If you want these values to be changing on runtime, there is a provision of relocating this vector table to some place in the RAM and so on. We will not be doing that in this course, but there is a register, there's a VTOR register which actually does that for you. So this is just as a side note. Now, so we see that this is an array of function pointers. Now, the first element of this array has to be the address of the top of the stack. Right? So this is to be the initial stack pointer. Now, the initial stack pointer is an address, okay, and this is an address of an array. This is an address of an array. So if this is an address of an array, and this is a set of function pointers that you are seeing here, if you have to include that value into this particular array, you have to typecast it as a void function pointer, and that is what has been done here. Void star unsigned long. This is what has been done here. Void star. Okay. So we are typecasting this array pointer to look like a function pointer, so that the compiler does not throw any errors. So that the compiler thinks that this is a function pointer only. But this is nothing but a value. This is nothing but a 4-byte value, which is the top of the stack, and we will see this value in the code. Maybe when we run the code next, we will have a look at this area of the flash. Next is the reset ISR. So this is the next in line. So the reset ISR is when the processor boots up, it loads the stack pointer and it calls the reset ISR. That is the first thing it does. So the reset ISR, we will be going in detail through the reset ISR, but right now just know that this is the reset handler. It's like an interrupt exception handler. So it goes into the reset handler. Then you have the non-maskable interrupt. So we have to put these names in the particular order, like so. So these have to be put in this particular order. And reset handler, NMI, hard fault. You cannot mix up this order, because this is the hardware understands this order for this particular processor, and this table will vary for different processors. The number of interrupts will become more will vary also. The order of the interrupts might vary. So the exception vector table has to exactly mimic this table, which we see in this reference manual. It has to exactly mimic this table. It is not necessary that you have to have all the interrupts. As we can see, all the interrupts are not installed here. We only have a few of them installed. Whatever we are going to use, rest of them can default to a default handler, which does nothing. It's just a while loop. So NMISR fault ISR. So here are some interrupts that we or exceptions that we need. For example, if you have a say memory fault, then this ISR is going to be called and it will get stuck in the memory fault exception handler. And then these interrupts are, so from the fault handler you have usage fault, and then system service, SVC call, debug monitor, pend SV sysdig. All of them are these interrupts. And these are all function pointers. So these are default function pointers, and then there are some blanks, in the sense this is reserved. So you'll see that these values are, some of these values are going to be reserved, usage fault, and then these fields are reserved, so it is not used. So these are filled with zeros here. So four words of reserved fields, and then again you have a few more interrupt handlers, or rather exception handlers. So let us see what exception handlers are there after the first gap, or the gap of 4 bytes. So you have a gap of 4 bytes here, and then you have SV call and debug monitor. So you have SV call and debug monitor here. This is SV call, this is debug monitor. Right now they are defaulting to a basic default fault handler, and then you have a place reserved, and then just above the sysdig handler you have the pend SV, which we are not using. So this is the pend SV, this is the pend SV, and this is the sysdig handler. Now the sysdig handler is something that we are using in our demos, so we will have the sysdig handler here. So sysdig handler is installed, so this handler has to be written somewhere, and the sysdig handler is written in a different file. Okay. And the respective interrupts for the sysdig handler has to be enabled, and you have to, and the respective code has to be written for these handlers. So going down, even though we are not using these interrupts, so they are for, say, RTC wake up. So they are for RTC wake up, flash RCC, EXTI line 1, EXTI line 2, 3, 4, so on. And then after ADC 1, ADC 2, ADC 3 interrupts, we have 4 reserved spaces. Now, if you see the manual here, the gaps that are shown clearly in the case of the events or the system events is not shown clearly here. So when you go through these numbers, you have to be careful about the jumps in these numbers. That is, when this shows the position where the interrupt is, that is the word position. So there will be certain jumps in the word position. So if you're not careful, if you go down, the beginning impression is that there are 86 interrupts, but that is not the case. For example, if you see the interrupt vector table here, or exception vector table, you have 4 gaps after the ADC1, ADC2 and ADC3 interrupts. So let us check out the gaps here. So we have, let us check where ADC1, ADC2 and ADC3 is, and then we will, so we have the DMA. So here you have the ADC1 global interrupts. Okay. So that is where what is written as ADC1, ADC2, ADC3. So from 18 you see there is a jump to 23 here, that the position 19, 20, 21, 22 are missing, but it is not so clearly shown as it is shown in the exception section where you have some reserved spaces. Here there are some jumps basically. So you have to be careful about these. So after ADC EXTI, you have the EXTI line interrupt. So after ADC, you have the external line interrupt, of course. But in the data, in the reference manual, if you're not careful, if you don't see the jump between the numbers, you will not realize that there is a gap here. So when you're writing your interrupt exception vector table, you may commit a mistake and not put the zeros here. Okay, so whatever is reserved has to be filled with zeros. And if you see this, if there is no clear marking here that there is a jump which is clearly not there, you may miss this out. So be careful about this. Let's see, go further. Then you have external line 9 to 5, timer 1 update, and timer 10, so on and so forth. So timer 1, timer 2, timer 3, timer 4 interrupts. Again it goes down, and then again there is a reserved space after USART 2. So if you again check the USART 2, let's see. So when you check the USART 2, so see 38, there's again a gap of one space here. It jumps from 38 to 40. So 39 is missing. So you have to be careful. Going forward again, you have other interrupts, and then again a gap of 4. If you check the documentation, you'll see that it jumps by 4. Again here it jumps by 1. So be careful about that. So these jumps have to be taken care of. And then it ends in SPI 5. So this is the exception vector table that you need to write. So you have to create a default interrupt handler for the interrupts that you're not using, which will be a part of this program, this particular file only. And the first, if you follow this technique, then the first one has to be typecast to a function pointer, though it is a pointer to an array. The rest of them can remain as function pointers. And you have to fill up the exception vector table this way. After filling, so let's have a look at the functions that are pointed to by here. So reset ISR is one very important function which we are going to go through in detail. So here you have the reset ISR, then you have the NM ISR, which is nothing but a while loop, then the fault ISR and the default int handler. This is the processor receives an unexpected interrupt. This simply enters the infinite. So you say you enable the interrupt, say TIM1 break and TIM9, and suppose you forgot to add the interrupt function handler here. So it will automatically jump to this function and it will get stuck there. So it will preserve the system state. Suppose you have done something and like that, and your system crashes or your system hangs, you can always check with a debugger what happened. And if you see that your control is stuck here in the default handler, you would know that probably you have not installed or you have not put the function pointer in the exception vector table. So those are debugging steps. Now this is extremely important. Whatever we are going to talk about now this is another very important, besides the exception vector table that we saw, another important functionality or task of the startup code is to prepare the memory regions for further execution. So we discussed about this, in theory, how the data section gets relocated and how the BSS section gets zeroed out. So we saw the diagrams, and we saw the diagrams about how the memory layout looks like before power up and then after power up, what happens. Now we talked about how the data section gets copied over to the RAM and how the BSS section gets zeroed out. Now that is done by this these few lines of code, that is writing data from the text section in the flash to the data section in the RAM. Okay, and this piece of code does the writing, zeroing of the BSS section out. But these lines of code look deceivingly simple, though there are some caveats. You have to declare the variables in a specific way for loop to especially work. This part of the code is tricky. Anyway, we'll talk about it in detail now. So what do we do first if we have to relocate the data, initialized data from the flash to the RAM, is what we are seeing now. So if you remember, we had used some variables, linker variables in the linker script file. We created some linker variables to keep track of some of the memory locations. So if we go back to the linker file, let us have a look at the linker file now, so that to just refresh your memory. So this was the start of the text section. If you remember, this was the start of the text section. So this was 80000000. Okay, this was the end of the text section. We don't know what it is. It could be any value, where the ISR vector was placed first, that is the vector table we saw. Then the dot text section, that is the code, whatever code we have, was placed, and then the RO data. RO data is nothing but the constant values. Okay, so the constant values means whatever variable you declare as constant will be placed here in the RO data section. This value is also constant. This value is also constant, but since we declared it as a separate section, so we created a separate section name for the ISR vector. It will go and sit in the flash first. This one will so this section, even though it is a constant, it will not be considered as RO data. It is a separate section in itself. So RO data are the constant values that you have, and then you have the underscore etext. So ideally, underscore etext has the VMA of the end of the dot text section. VMA of the end of the dot text section. Underscore text has the beginning, VMA of the beginning. So we discussed about the difference between the LMA and VMA, if you remember. So this holds the beginning of the VMA of the dot text section. Now we will have to, in the first part, that is where we have the initialized variables which are global, okay, need to be relocated. So the constants need not be relocated. The constants are wherever they are, but just after this section you have the data section. Okay, so in this data section, as we saw, was split into VMA and LMA. In the past you saw that, so it was split into VMA and LMA. So we have to actually grab the LMA address, that is the address where it resides in the flash, and keep copying those values into the VMA, that is the RAM. So if you have your flash here, that is the LMA address, which is immediately after the RO data. So you will have some data immediately after the RO data, and then you have the VMA, that is your RAM. So VMA starts from SRAM. So your VMA is going to start from this address. So the job is to go to the LMA, pick up the data from the LMA. Okay. So and the LMA address is this one, etext, because etext holds the address of the LMA of the next section, because etext points to the address next to the end of the data here, right? So etext is going to have the LMA address. Underscore data is going to have the VMA address. You have to be very careful because up to here LMA was equal to the VMA. There was no split. So we can take this as the VMA or the LMA. So we will grab the right address here, okay, because this is the end of flash where the initialized data prior to boot up is located. Okay, so the data section, and we spoke about it, but we have to move it to the RAM. So if we take this address, this is the new VMA. That is where it has to be moved. So the logic is let's see the logic here. So if we are clear about that, the code will become very easy for us. So if we take this address, this is the LMA, that is the end of the flash, the beginning of the data section. That is where you have your, so before we saw that before booting, this is your text section and auto data section, and there is a small narrow section here, which narrow, or it could be in any width. In our case, it's a narrow section. In this section, we have the initialized global non-constant data declared here, and the start of the section's address is underscore etext. This one, okay, this is the address of the start of this section, and we have to keep going up like this. And we have the data section. So we have the data section, and the start of the data section address is 2000, sorry, not 2000, whatever it is, 2 with 7 zeros. This is the underscore data, okay. This is the underscore data address. So we will create a variable which points to this location first, etext, okay, and we will create another variable which points to this location, okay, and then we will go ahead and keep incrementing this variable in a for loop. This variable, the variable that is linked with underscore data, in a for loop just till before edata, because edata contains the address of the next empty section, right? So the data completes before edata. So what we do is we take this address, keep incrementing it until we go one address short of this. So we keep incrementing this until we fall one address short of edata. When that happens, we are done. So every time we jump one address, we copy one value from here to here. Again, we jump one address. So when we jump one address, what we do is we increment this pointer and we increment this pointer as well. Whatever the data is pointing to, increment that pointer as well. So we don't keep a counter here. We do not know how many, we do not care about the number of amount of data we have here, because we don't need to, since that number is, the data section keeps track of that number. So the assumption is we have the same amount of data here and here. Obviously, that is what the linker has done. It has just kept that data here. So if we jump, say, 10 places here, we assume that of course there will be 10 words or 10 bytes of data or whatever mentioned here. So what we do is we keep jumping address to address and keep copying. This is done in a for loop, and this is the first part where the data section is copied from the flash to the RAM. So this is the VMA, and that at has also made the data fall on the RAM to be for preservation between boot ups. Okay, so that is the first logic. So let us have a look at the first part of the code, and then we will go to the second part of the code. Now the second part of the code is tricky. It needs some explaining. So we'll see that. So let's rub this out. Let's go here. So these are the variables that we just saw: etext, data, edata, bss, ebss. So let's have a look. Etext, data, edata, bss, ebss. So here are the variables. Okay, etext, and there is underscore text, which we are not using here. We are only using etext, data, edata, underscore bss, underscore ebss. So that is what. And since these variables are external to the main, or sorry, the external to this module or this file, we have to give external. And one thing is, we can declare, we can typecast this data to anything. So we have cast it to char. Now typecasting it to char has one disadvantage, that is the data copy will be taking more cycles. But one safety with this is, even if your data is misaligned, if it's a char, then it is not a problem. The data still gets copied over. Okay. Now let's come to the code as we saw. So we declare two pointer variables and 2 pointers to char, so character. Okay, so it is pulsrc and puldest. So pulsrc is where the data is residing in the flash. So we have, as we saw, we have to copy it from the flash to the RAM. So this is the data that is residing in the flash, and this is the data that is residing in the it is the destination copy position. So in the destination copy position, we give the address of data. And if you remember, we talked about that, putting an ampersand before the linker variables. So we have to do that. So what it does is, it's a for loop. It starts from here. So this is the RAM location. So it starts from this RAM location and it goes up to where it is just short of the edata. So that is what happens in this for loop. And so this is your destination. So we do a post increment, star pull dest equal to star pull src plus plus. So star pull src means one data from the flash is now copied into the RAM location, this to this, and then both increment. So both are pointing to the next location. So if you have, this is your flash data, whatever units of data, words or bytes or whatever. First, say it was pointing here. Next iteration, say this variable is pointing here. This one is pointing to this location. So this is pull src and pull dest. In the next iteration, what happens is the pointer moves to the next location. Next iteration, the pointer moves to the next location, and once a pointer comes here, the data, of course, it keeps getting copied like this. So this is where the data gets copied. Now, as far as C is concerned, whenever you are declaring some information data within a function, it is going to be using the stack. Now, the interesting part is, the stack has not yet been set up. That is, the stack location is there, but it has not been zeroed out yet, because the BSS zeroing out of the stack happens here in the next loop. But we are still using the stack here. Okay, we are still using the stack here, because when we declare these variables inside the function, these will be using some stack spaces. And then, of course, we copy over the variables. Once this is done, we come to zeroing out the BSS section. Now mind it, when the BSS section gets zeroed out, it is zeroing out the stack also. Now all variables within a function is placed on the stack in C. So when this section gets zeroed out, these variables, whatever we had declared, actually gets overwritten. These variables get overwritten in the memory. They no more exist, or they don't exist the way they should. Their values are corrupted. But that doesn't matter because we don't need these variables anymore. Had we needed the variables later, then we'd have to be careful, because then we'll probably have to declare it outside as a global variable. So this part is quite tricky. That is the loop which zeroes out the BSS section. Now this variable that you see, this pointer variable, is not initialized within the reset ISR function. Now there is a reason for that. This is an unsigned char, and it is actually declared as a global initialized variable outside this function. Now if we had declared this as a variable local to this particular function, what would have happened is that variable would have been stored on the stack, and this function actually zeroes out the entire BSS section including the stack. So what would happen is, as this goes on initializing the BSS section, it would erase itself and this loop will fail. That is, assuming that this is the stack area, and this, since if it were a local variable, it would absolutely have to be declared within this stack area. And this function, the job of this function is to zero out the stack area, initialize that segment of memory, and it would actually erase itself. So it'll be something like shooting itself in the foot. And either you will see, if you have this code, your processor will not boot up and it will crash. So you have to be careful. So the remedy is to use pure assembly. So you could use pure assembly to address the issue, or you could declare this variable outside, as we did, as a global variable, global and initialized variable. So if it's a global and initialized variable, this goes into the data section, right? So and this part of the function actually copies that variable into the data section. So when we do a copy over, this variable is actually copied over to the data section, this one. So this one is important. This part, the order of this is very important. You cannot have this first and this next. This one actually moves the data over to the data section, and then the BSS, because if say you ran this one before this one, again the program will crash, because this will try to look for the variable within the RAM and it will not find it. Okay, and so then that is a problem again. So this order is important. That is, this has to run first and this has to run next. Now, how does this code work? This variable is assigned the address of BSS, and this address is assigned twice. Once here because it has to be an initialized global variable so that it forcefully goes into the data section, and then it is assigned once again here inside the for loop. And again, this goes from, if you look at the linker file, it goes from here to just before EBSS. So it just loops between these two areas and keeps filling it with zeros. That's all it does. So it just loops between goes from BSS to just one before EBSS. So one memory location before EBSS, it goes memory location by memory location, and it goes byte by byte and keeps making it all zeros. That is the job of this particular function. But as I said, it's pretty tricky. Do not have this variable declared within the startup function itself. Otherwise, it will stomp on itself and delete this variable, and your function is going to crash. And then once that completes, once the initialization completes, this jumps to the main function. That is, it goes to your build example main. So the build example main function that we have been seeing here, it goes there and it runs here, and all the peripheral initialization and processor initialization, clock setting, all of that happens here. And that's not a part of the startup. The startup is only responsible for doing this, and this is extremely important, this part. Without this, the processor will not work properly.